Hello, this tutorial is going to be about a CFD analysis on an airfoil. This was recommended by one of my subscribers called Zoya Rizvi, and for you Zoya I'm gonna do this tutorial. So as always we start with drawing the fluid domain, and in order to draw the fluid domain we have to choose whether it's 3D or 2D. I'm not going to simplify it for you, Zoya, so I'm going to make it as a 3D fluid domain. So first of all, we go to rhinoceros and we check an airfoil profile on Google. Let's say this one. I'm gonna save the image. Gonna go back to rhinoceros and picture frame. Okay, we can't import a GIF file, so we'll have to choose another picture, unfortunately. So I am going to choose this one. Is it a GIF as well? Oh, come on. This is how I lose most of the time. Okay, this is a JPG, so I'm gonna save the image. Selected. It's 40 meters. Of course it's not gonna be that much, so I'm gonna scale it and I'll make it out 1/50. No. So it's around 0.76 meter. Okay, this is acceptable. 0.76 meter. Or we can scale it a bit more, like that. That would be enough. The next step is to draw the curve. Okay, remove the author file. Okay, we delete this, we put it as a wireframe, we patch it, and now this is the boundary layer of the airfoil. I'm going to extrude it. Rotate the object. That's it. This is the airfoil. And what's gonna happen now is this. We are going to draw the fluid domain, put it in the middle, so over here. So the airfoil is inside, let's say, the duct where we are going to make the CFD animation, and the airfoil is the boundary layer, so we will have to subtract it from the air duct, and we're gonna do that on workbench because we can't do it over here. So the next step is to file, save as, step file, and I'm going to call it fluent domain. Yep. After saving the file, now we go to the Alice computer system and we import our file to Workbench. So we'll go to the command bar, and Workbench. If you have your Fluent installed on your laptop, you don't have to access any other computer anyway, so forget about the command line that I just wrote. So the next step is to mesh our fluid domain, but first we have to deal with subtracting the airfoil from the fluid domain, and we do that by going to geometry, right click, oh, come on, I'll have to tell you from now that in CFD analysis there are so many methods that you can use in order to simulate a case. In your case, LES method is the best method that can be used, but the problem with it is that it consumes a lot of time. Like, it requires really a long time to get you an answer or a solution, and it requires a high computer performance levels and high memory and multiple processors. So in order just to save time, I recommend you to go for RANS method if your tutor or your doctor accept it. And in order to do that, you will have to choose one of the models offered by the RANS method, and one of them is called K epsilon, which is a good one. So I go to yes meter, and now I go to file and import external geometry. We go to desktop and domain. We go to import and generate. Okay. So as you see, we have two parts bodies over here. One, which is the duct, and two, which is the airfoil. What I am going to do is to go here, tools, and just give me a sec, boolean, and in the boolean we have to choose subtract. Target body is this one, target body is taking a lot of time. So the target body, this one, come on. Okay, the tool body is, let's first hide this one. In the tool body, this one, and apply. And after doing that, we just go to Boolean and generate. And now show body. Right. As you see, there is a groove inside the fluid domain, which is over here, which is the airfoil. Okay. So the next step is to just keep it over here and go to mesh. Okay, so this is the mesh tool in the workbench, and we're gonna use CFD. There are so many methods in meshing, and each one has advantages and disadvantages. I'm not going through them all. I'm going to choose one method, and you will have to read about it to make your research about it and see what are the differences between each kind of mesh. Anyway, there are so many programs as well in meshing, and not just the tool offered by Workbench. There is another there is another program called ISMCFD, and it is offered by Ansys as well. It's more complicated than the tool offered by Workbench, but it gives more options. So I recommend you to have a look on it. Okay, so what's going on now? Alright, I'm gonna choose OK. And the system is very low today. And tetrahedron, go to the mesh, go to sizing. Sizing, it determines the size of the mesh. We are going to choose it as fine. No, we have to choose it as, and I'm gonna try now, just update the mesh, see what will happen. Okay, it could not be generated, whatever, and I'm gonna remove this one, delete it. Okay, on curvature, I'm gonna update now. Okay, so it is meshing. What's wrong with it? The system is very slow for some reason, I don't know. Probably the internet connection is slow, that's why. Anyway, so we have a problem in the mesh, and it has to be C3 -2. Alright, and let's go to mesh and update it. Please, please, please work. Go on. Alright, we've got a mesh. That's cool. Okay, I want just to tell you about something. I'm not going to work on it over here because it requires a long time. Don't think that CFD simulation takes 10 to 20 minutes to just finish it. It requires a long work, and it requires a lot of concentration. The thing is that on the wall of the airfoil, the mesh should be very refined, and this requires a lot of cells over there in a smaller size. So I'm going to check the quality of the mesh on the wall boundary by making a section plane, if the freaking computer let me do it. So low. Please, come on. This is so annoying. I'm sorry for it being slow, but it seems my connection to the university is slow. Okay, so we couldn't see anything over here, so we have to make another slice plane, unfortunately. So I'll take this one and I will do another slice. Yeah, I'm gonna pause it until it just right, because I don't want to waste your time. I'll wait. Come on, darling. Okay, let's see if we can see anything. God's sake, we can't see anything. Anyway, let's do another section and wait. Okay, after long trials, I've come up with this figure. As you can see, the airfoil over here, the wall boundary is not well refined, and the thing is, it is only refined at the corners. So from 1 to 10, I consider this mesh as equal as to 6 or less. It's not a very good mesh, but anyway, we don't have time to work on like increasing the refinement of this mesh, because this, as I said before, requires a lot of work. Anyway, so I'm gonna continue from now on, and I will just remove the slice. I will exit this thing, and I will file. Oh, before I do anything, we have to assign the boundary conditions, the inlet and the outlet of the duct. In order to do that, we must have a fast connection, which I don't. So we go to the mesh over here. We we go to this. We select the face option. And we go to this face. When you right click, we click first on it, and then we right click, create named selection. We call it inlet because the flow is going from, what the hell happened? So annoying! Okay, I'm going crazy right now. Create name selection, and we call it inlet. Okay, as you see, we have a boundary. Now we rotate the object. So I was saying that the flow goes from X, it goes with the X direction. Now I select the other face. Right click, create name selection, and we call it outlet. Okay. So we have the inlet and outlet. Now we go to File, Export, and save it as fluent input mesh. I'm gonna call it not in rents. And only desktop. And we're gonna call it airfoil and save it. It's good. Now let's close this freaking window. That's a great relief, to be honest. Exit. And where is it? It's over here. That's good. So let's go to Open Terminal now. Module, load, fluent. It is a 3D program, double precision, and OK. And release the fluent program. Now we have to import the mesh. So we go to read mesh, and in desktop, this is the desktop, airfoil. Okay, excellent, that's excellent. You can see it is a duct with an airfoil inside of it, and the flow will have to go from in the X direction, and this is the inlet and this is the outlet. Great. So we go to model now. We choose the model as I said earlier. I'm not going to make it as an LES because we need a very supercomputer and it would take a lot of time. Large eddy simulation. You will have to read about the subscript scale models, Smagorensky, Lilly, and there are so many other in the large eddies. If we choose the large eddy simulation, I mean, there are so many wall models, and there are so many wall treatment as well, so you have to read about that. As for the K-epsilon method, we have 3 models, the standard one, RNG, and realizable. You can read them in Fluent guide catalog. I'm gonna use the standard one, and it is a Rance method, by the way, so I'll choose OK, and then go to the material and choose the fluid as air, and solvent condition fluid, edit, it is air, and the boundary conditions in the inlet side, the velocity n, we'll add it, it's an absolute velocity, and we can choose it as, I don't know how much an airplane goes. What is the speed of an airplane? Let's see. Okay, we have to look at that. Let's go to Google. Okay, forget about my Facebook. Google, and the speed of, what is it called? Cessna. In meter per second. So the speed of a Cessna, speed over here. Okay. Converting from the standard 3-blade propeller to small diameter. Right to hand in. Increase. No, that's not what we want. wait, airfoil, stall speed, cruise speed. It is 480 kilometers per hour, so 80 airfoil 8. Okay, so let's go to converter, convert 1 to 3, and go to velocity. Come on, velocity. We choose it from kilometer per hour to meter per second. So how much is it? It is around 480. So it's 133 meter per second. Wow, that's so fast. Okay, that's too fast. Anyway, 133 meter per second. Right. I'll choose OK. I'll set the outlet, which is the pressure outlet. Edit, and I'll choose it 0 because it's an atmospheric pressure. And now I go to solution method. You have to read about each one of these things. For more accuracy, choose second order upwind, for example, and similarly for the other things. Solution control as well, you will have to read about under relaxation factors and what and how does these values affect the convergence of the solution. We go to monitor. So we want to study the drag and lift. So what we are gonna do is, first of all, roll zone 1. The roll zone, let's see in the boundary condition how many roll zone we have. So if we display the mesh, and I only want to display the wall. Yeah, so this is the wall. So what we want to study in the monitor for the drag is roll zone, plotted, and right, force vector. We can choose a force vector for in the x, y, and z direction. I'm just gonna select the x direction. On that, I don't mind. Alright, we choose OK. Lift as well, we do the same thing. Right. Okay, it's in the y direction. Okay. Go to solution initialization. We choose it from inlet side. We initialize. And we go to calculation activity. Enter. Forget about the data file. Create edit. And we choose the font commands. What am I doing? No, that's not what I want. Calculation activity. Oh yeah, I forgot to do something. We chose a time to be steady, so it's going to give us the final state of this animation, or at equilibrium. I recommend it to be transient, but in order to make it a transient case, we will have to work on the time step and how many time step do we need to make a simulation and for how long. So it's a long story, but you can do it as transient case. So I'll stick to the steady case right now. And solution initialization, we did it already. Calculation activities, and up. Let's see this. No, thank you. Let's see. No, I'm not going to animate anything. And I think that's enough. Let's go to the run calculation. Number of iteration, let's put it as 300 first. And report a table, okay, number, and now we can actually calculate. Oh, so this is a lift convergence. We can scale residual, that's what we want, to be honest. Okay, so it is converging, I think. We need to reach the 10 to the power minus 3. So I'm gonna pause the video right now and return back to you. Okay, so as we see, the calculation has been completed and the solution has converged. What we can do right now is go to graphic and animation and continue setup. So what actually do we have over here? Can check the pressure if you want on the wall zone. Display, compute and display. Okay, so we go to temperature, hold on pressure, display pressure, and we come here and put the level as 100, display. And as we can see over here on the airfoil, the pressure levels, as it is expected, the pressure level on the upper side should be less than the pressure level on the lower side, and this what would create the lift, because the pressure upside is lower. So what we can do is check the total pressure. Yeah, in the total pressure I expect it to be the same because the velocity pressure is included inside. Okay, let's see the velocity. Okay, someone is let's check something. Okay, I don't understand what is this anyway. Just forget it. Close. And so display mesh. display, close, right? So we've seen the pressure, which is the most important. Now let's go to solution control, monitors, and in plot, edit, curve, apply. Close and plot it. Okay, so I found another way to just check the forces. We go to reports, we go to force, and we have to select the wall, and for example choose the direction as 1 and print it. So in the x direction the forces from pressure is 1083 Newton. So this will cause drag. The viscous forces and the total forces, and as we see, we can select, for example, to see if there is lift at 133 meter per second. We go to Y and select 1 and print it. As we see, we have the forces is minus 0.1, minus 0.2, and the total is minus 0.39 Newton. So at 133 meter, the net force in the y direction is minus 0.391 Newton, which means there is no lift. Well, what are the reasons for that? The reason is the airfoil itself is probably not too long when I made this simulation. So if we make it longer, then the forces, then the pressure under the area will be higher, and this will create lift. So we are too close to a neutral force, and if we probably make the airfoil longer, it would be a positive number, and this would suggest a lift. We can check the moments and the center of pressure as well in the same way. So this is how you can select your or check your forces according to the direction of the vector. And there is something else we can do, is checking the turbulence. Okay, and check the turbulence intensity in the wall zone. And as we can see over here, the highest turbulence levels are occurring over here. And this is expected, I think. What else can we check? So we check the pressure, we check the turbulence intensity, we check the forces, and we can check as well the wall shear stress. Let's see the X wall shear stress display. Can check it over here. So as you can see, at this area it is the lowest, and at the horizontal and at the semi-horizontal area the values get higher. And we can check the Y shear stress display. Alright, so in this tutorial we have learned how to extract the net forces from an airfoil, how to extract the wall shear stress, and how to plot them. And we have learned how to plot the pressure distribution over the airfoil. Although I just want you to be aware of this information, that a Rance method for such case is not recommended. What is recommended for such case is an LES, large eddy simulation method. Alright? And I did the Rance method only because I can't make a long video, and I can't just like work on the university computer for a long time. And the difference between large eddy simulation and the Rance method simulation is huge. In the large eddy simulation, it's not a time average method, so you would see a live simulation during time. As for the Rance method, it is a time average method where at some point, even if you put it as a steady case, unsteady case, the average, the velocities in the streamlines will get averaged and become constant, and that's not what we want. Anyway, thank you for watching my video. Please try to subscribe to get updated for a new simulation and new tutorials. If you have any questions, please put them in comment section and I will answer them. Okay, take care of yourself. Bye bye.